We're here in section 8.3, problem number 1. We've got a random sample of 40 binomial trials, and they resulted in 16 successes. Test the claim that the population proportion of successes does not equal two-tailed test, right? 0.5? All right, so let's see, and use 0.05. Part A says, can a normal distribution be used for the p-hat distribution? Explain. Well, we're going to be able to use the normal distribution if, right, we have to say if n times p is greater than 5 and n times q is greater than 5. Now, actually, all right, n times p, this I think is going to be a little bit redundant here, because if I look at, this is really p hat, because that's the only thing I have here, is n is 40 and p hat is 16 over 40. The 40s are going to cancel, and I end up with 16, which is greater than 5, right? So this is 16, so NP greater than 5. Now, we need Q. All right, so if P hat is equal to 16 over 40, which turns out to be 0.4, Q hat is then 0.6, and then if I run this one, 40 times 0.6, that's 24, which is greater than 5. All right, so both NP greater than 5, NQ greater than 5. All right, so that implies we can use the normal approximation. So I do like that the problem started out by asking us if we meet the conditions. There's no sense in continuing the problem if the conditions aren't met. So we're going to select this item right here. Yes, NP and NQ are both greater than 5. Now, the next part, state the hypotheses. Well, the question says this. Test the claim that the population proportion of successes does not equal to 0.5. All right, so that's going to be H naught. So that's going to be what? H sub A, our alternate, is not equal to, so it's a two-tailed test. Let's run down here. Do you see any two-tailed test for the alternate? There's one right there. So this says that the alternate, or the proportion, is not equal to 0.5. The opposite would be that it is equal to 0.5. So we're going to go with that selection right there. Now, part C says compute p hat. We really already did that. P hat is 16 over 40, which is 0.4. Now, this part down here says compute the corresponding standardized sample statistic. Now, we're using the normal curve, so what we're looking for here is Z star. Now, there is a formula for making that conversion from P and Q to Z star, but instead of using that, let's just go straight to the calculator and run a hypothesis test, because when we run the test, all that data comes up, right? All those statistics come up. So let's just do that. So let's go right to stat. So press your stat key, and then you want to arrow over to tests, because we're going to run a test here. And then you want to scroll down to number 5. We haven't used this one yet. Number 5 says one prop z-test, one prop proportion, one proportion z-test. So we're testing one proportion with a z test statistic. So select number 5. Now, some things come up here. What comes up is P naught. So what we're asking here is, what are we testing here? We're testing 0.5, right? We're testing that the hypothesis P naught, H naught says that the proportion is 0.5. Our X value is 16. Our N value is 40, right? 16 successes out of 40. And the problem has us doing up here at the top left, a not equal to test. So they're telling us, let's just run a not equal to test. So put your cursor right on the not equal and press enter to fix it. And then go down to calculate and press enter. Calculator comes back with this information. Now it tells us, okay, here's what we're testing, right? That it's not equal to 0.5. It gives us the z star value, and that just happens to be what we're looking for here. So let's type that in, negative 1.26. So we'll put in negative 1.26. Now, it turns out we're not going to use that value. That's the value you would use if you were running the, say, the traditional or critical region method, but we're not using that. We're using the p-value method. So let's go on to part D. Part D asks us for the p-value. Now, the p-value we've got right over here. There's our p-value, 0.2059. So I'm going to put that in here, 2059. Now, it's that p-value that we have to think, okay, do we reject H0 or would we fail to reject H0? And sure enough, that's what they're asking us here. Do we reject or fail to reject? So I always do this by making a little table here. So here's P and here's alpha. Okay, I make a comparison. Now the P is 0.2059, almost 20%, 21%. Alpha, we're given that as 0.05, and 20.59% is bigger than 0.05. So do you remember what to do with that? If it's a greater than, you fail to reject H0. So we're not going to reject H0. So we're going to fail to reject H0. So let's go down here and see which part we're going to go with. So we're going to fail to reject. So let's see, what do we have? This says reject. This says reject. So toss these out. These are two failed to reject. So which one are we going to use? At 05, we fail to reject H0 and conclude that the data are statistically significant. That's not true. If we fail to reject, that means that there's no statistical difference between these two numbers, right? We've got really two numbers. Here's what we have. We have the 0.40 and we have the claimed 50, all right? This is the observed value. This is the claimed value. Well, we're saying that we're going to not reject this. We are not rejecting this. So even though there's a numerical difference between these two, it's not significant. The numerical difference can be attributed to just chance variation in the sample, right? We sampled 40 individuals. Now maybe if we'd gotten another 40, a different 40, or 400, this number would be very close to that number. So we're saying there's no statistical difference between those numbers. So we're not going to go with this one down here. So what's the last one? Oh, we're down here. At alpha equals 05, we fail to reject and conclude that the data are not statistically significant. So if you fail to reject, no significance. If you reject, then they are significant. So let's go with this one here. Now, so what does that mean? We're going with this one, right? That we fail to reject and conclude there's no statistical difference. So we're failing to reject this. So we're essentially going with this. So which one of these is down here? It says, I guess I have to read them all. The sample, p hat, all right, that's the 0.40% based on 40 trials, is not sufficiently different from 50% to not reject. Wow, that's a lot of negatives in there. To not reject. Okay, I better keep reading that. I'm not sure I understand what they're saying. 40% based on 40 trials is sufficiently different. Well, that's not true. We're saying it's not sufficiently different. So forget these two down here. Go to the last one. The sample p hat value, 0.40, based on 40 trials is not sufficiently different, right? We're saying there's no significant difference to justify rejecting. There it is. We cannot justify rejecting H0. All right, so we're going to go with this one right here. That's the last one. And that is the end of that problem.